All right, so well, thank you for the invitation to speak. So the title of the talk is Homology, Cobordism, Local Equivalence. It is joint with Matt Stoffregen, who is here in the audience. So this talk is really going to be about computations of involutive Floer homology for certain three manifolds. But I thought I would begin by giving some sort of topological applications of these computations and explaining in general what sorts of questions you can use involutive Heegaard Floer homology to answer. Okay, so the principal object of study for this talk will be the homology cobordism group. So we probably all remember, so this consists of all integer homology spheres, and then I mod up with a relation of homology cobordism, where y1 and y2 are homology cobordant if there's a cobordism between them that homologically looks like a cylinder S3 cross I. Okay, so and this set has a group structure where the group structure is given by connected sum and inverses are given by orientation reversal. So let me review some facts that are known about the homology cobordism group. So perhaps the most famous fact is that there's a mod 2 valued invariant defined on the homology cobordism group. This is the Rokhlin invariant. Okay? And maybe the most famous theorem about this most famous fact is due to Manolescu. So if I have some integer homology sphere whose Rokhlin invariant is 1, then I actually know that this is not 2 torsion in the homology cobordism group. Okay? And not particularly related, but well, how large is the homology group, cobordism group? Well, it turns out pretty large. Okay, so in particular, we know the existence of Z infinity subgroups of theta. Okay, so originally this theorem was due to Peruta and also Tuchel and Stern. And nowadays you can exhibit many Z infinity subgroups using equivariant monopole Floer homology and so on and so on. Okay, so but it turns out that these three facts actually summarize a lot of what is known about the homology cobordism group. So sort of embarrassingly, we don't actually know very much about the homology cobordism group. So let me write some of my favorite questions. So the first and perhaps most famous question is there torsion in the homology cobordism group? And this is unknown. Okay? We have no idea. Okay, so in view of this theorem of Manolescu, you could specialize slightly and say, I could restrict to things with Rokhlin invariant 1. So is there Rokhlin invariant 1 torsion? Okay, so we know that there's no 2 torsion, but there could be, for example, 4 torsion or 8 torsion or something like that. And this is also unknown. Okay? And the second question is that I am fond of is, do Seifert fibered spaces, for example, generate the homology cobordism group? So let me write this as theta SF. So this here is a subgroup of theta generated by Seifert fibered spaces. And is this actually equal to all of theta? Okay, so this is probably not true. So maybe I should put not equal. So I should note that, so it's a theorem of Meyer's that any homology 3 sphere is homology cobordant to a hyperbolic manifold. So of course, hyperbolic things generate the homology cobordism group. The analogous statement for individual Seifert fibered spaces is not true. So, so it's a result of Matt and also Freushov that basically if you take 2 Seifert fibered spaces and sum them together, then usually you don't get something that looks like a Seifert fibered space, even up to homology cobordism, right? But it's still possible that Seifert fibered spaces generate the homology cobordism group. Okay, so here are just some open questions, some properties. So today, how are we going to study the homology cobordism group? Well, studying homology cobordism group directly is too difficult. So instead, what we're going to do is we're going to construct a homomorphism from theta into some other mysterious group. Let me call it J. Okay, and then we're going to study the image H of theta. Okay, so this construction of this homomorphism is not due to me. So this is due to Hendricks, Manolescu, and Zemke. And it uses the machinery of involutive Floer homology. So I wanted to let me begin by giving a bird's eye view of the thing that comes out of the machine of involutive Floer homology. How do I define this group and this homomorphism? Okay, so for now there are 3 important properties. Okay, so the first is just that, well, if I have y as an integer homology sphere, let me just establish some language, then the involutive Floer homology machine is going to spit out for me some sort of algebraic invariant, which I'm going to call an iota complex. Okay, so I'll define what all these things are in a moment. But so maybe an iota complex up to homotopy equivalence. So just like in Heegaard Floer homology, you give me a three-manifold, I spit out for you a chain complex up to homotopy equivalence. Involutive Heegaard Floer homology, you give me a three-manifold, I spit out some other algebraic object, which is called an iota complex. Okay? And important property is that if I have a homology cobordism between two three-manifolds, that induces a particular relation between their iota complexes. There's some mysterious algebraic relation, which I'm going to call local equivalence, such that whenever y1 and y2 are homology cobordant, then their iota complexes are locally equivalent. Okay, and I'm going to define this notion in a moment also. And then the last fact is that this theorem due to Hendricks, Manolescu, and Zemke, well, turns out there's a notion of tensor product on the set of iota complexes. And if I take the connect sum of two things, then their iota complex is tensor product. Okay? So what is this group J here? Well, so J here is going to be out of all possible iota complexes. So this relation of local equivalence. Okay, and it turns out that tensor product operation plays nice with the notion of local equivalence. The tensor product operation actually gives a group structure on this set. Okay? And then these properties that I just wrote down here are exactly saying that the taking of the iota complex of a three-manifold is a homomorphism from the homology cobordism group into this terrible algebraic group, which is defined as the set of all iota complexes, and so on and so on. Okay, so I mean, I haven't really said anything. All I said is this map is sort of given by taking the involutive Floer homology. But the point is the set of iota complexes has a group structure. Okay, and I had to describe this fact because I want to state a particular theorem. All right, so the theorem, the main theorem that I want to talk about today, okay, is a structural computation of the involutive Floer homology for Seifert fibered spaces and sums of Seifert fibered spaces. Okay, so the theorem is the following. So H of theta SF z infinity. Okay, so this is just I compute. So theta SF here is a subgroup of theta. As I said in the question, maybe all of theta, probably not. And we just compute the image of this under this homomorphism, and it is z infinity. Okay? And this is a very explicit z infinity. So let me make a few comments. So, okay, maybe comment number one. So we have sort of an explicit basis for this z infinity. Okay, so if you want, turns out that, so let me define this yi is an iota complex. This is the image of, I think, 2i plus 1, 4i minus 1, 4i plus 1. And this is for I greater than or equal to 1. And then let me also throw in the image of the Poincare here. And it turns out that these complexes form a basis for this z infinity. Okay, so another way of saying this is sort of curiously, from the viewpoint of involutive Floer homology, any linear combination of Seifert fibered spaces might as well be a linear combination of these particular Seifert fibered spaces. Okay, now it's not clear whether there's sort of something topologically important about these particular. It's more of a fact that like they happen to have a convenient, like their involutive Floer homology happens to form a convenient sequence. Okay. So the second remark I want to make about the theorem is that we sort of have some sort of decomposition rhythm. That is to say, if you give me a sum of Seifert fibered spaces, then there's a fairly straightforward combinatorial procedure where I can compute for you, the image of that element in my z infinity with respect to the spaces. Okay. All right. So, are there any questions about the statement of the theorem? Okay. So maybe I should make a note. So I should make an unfortunate note because nothing in life is free. So the kernel of this homomorphism is not 0. Okay, so there are elements which you can show sort of have trivial Floer homology, but I think maybe using instantons, you can show that they're non-trivial in the homology cobordism group. So the kernel of H is not 0, but what is H good for? Well, it's like any other invariant. Like if you give me y1 and y2, which are in theta SF, and I want to obstruct homology cobordism between them, then it suffices just to compute their images in this Z infinity and see that they're different. Okay? And so that's why it's sort of important that this is like a practicable thing. But in particular, suppose I have some class y in theta SF, and I compute its image in this Z infinity, and I see that it's non-zero. Well, then, because H is a homomorphism and Z infinity has no torsion, then y better not be torsion. Okay? So this idea actually leads us to the first application of this theorem, which is theorem. So it turns out that if the Rokhlin, so if y is in theta SF, and the Rokhlin invariant of y is 1, then you can actually, we prove that the image is non-zero. Okay, so this establishes that y is not torsion. Okay? So this is a partial answer to question 1.1. So we answer question 1.1 negatively amongst sums of Seifert fibered spaces. Okay? So we actually proved something a little bit stronger. So for people who are sort of more familiar with invariant, homology spheres, so we actually proved a slightly stronger theorem about the Neumann-Siebenmann invariant, which is, let me just write it here. So the Neumann-Siebenmann invariant is an invariant for plumbed three-manifolds, which is not known in general to be a homology cobordism invariant. But we actually show that but we actually show that if you have a sum of Seifert fibered spaces, then you can compute the Neumann-Siebenmann invariant from the image in this Z infinity. Okay, and since the image in the Z infinity is a homology cobordism invariant, then that implies the Neumann-Siebenmann invariant amongst sums of Seifert fibered spaces is a homology cobordism invariant. Okay? So here are some applications of this computation. So maybe I'll also say one sort of extra thing relating to the second question I've written here is, here I've sort of told you, well, we sort of have an explicit understanding of the involutive Floer homology of sums of Seifert fibered spaces. So if you wanted to find something that was not homology cobordant to a sum of Seifert fibered spaces, then you would just have to produce something whose involutive Floer homology does not look like something in the Z infinity. Okay? So that's one way you could attack this question. All right, so maybe I'll also make a note. So I mean, the way to think about this theorem is this is really a complete calculation of the involutive Floer homology of these manifolds. So, if you know something about the involutive Floer correction terms, the upper and d-lower and so on, all of those are invariants which are derived from the local equivalence class. So this computation is, you can compute the upper and d-lower and so on from, the basis decomposition in the Z infinity. Okay. All right, are there any questions? Sure? Sorry, this H map? No, it's not injective. I wrote this somewhere. Maybe I did not write it somewhere. Yeah, so as I said, there are things that are sent to 0, but you can show they're not trivial in homology cobordism. All right, so let me give a sort of brief overview of involutive Floer homology. Or involutive Heegaard Floer homology. So this was sort of done 2 days ago, but 2 days is a long time. So, all right. So the setup that we'll be dealing with today is, suppose y is an integer homology sphere. Okay. So remember in Heegaard Floer homology, if you give me this, then I give you back. Let's take the minus version, some chain complex. Okay. And this chain complex depends on choosing a Heegaard diagram and some additional data. So I've written this H here to denote the dependence on the Heegaard diagram. So, I mean, let's just remember. So here is the greatest Heegaard diagram of all times. Okay, so let me get some colored chalk. Orange and green. So okay, so fine. I have some alpha curves and some beta curves. Okay, but there's actually another Heegaard diagram which is tied for the best Heegaard diagram of all times, which is almost exactly the same Heegaard diagram, except that, of course, I switch which curves I call the alpha curves and which curves I call the beta curves. Okay, and also, so there's also some choice here of almost complex structure on the symmetric product. And here, I'm going to choose a conjugate almost complex structure. And I'm also going to reverse the orientation on my surface. Okay, let me call this sigma bar. Okay, and I'm going to denote this choice here by h bar. So this is like the conjugate Heegaard diagram. Okay, and the point of involutive Heegaard Floer homology is that there's actually a map, a chain map that goes between the Heegaard Floer complex with this Heegaard diagram and the Heegaard Floer complex with this diagram. Why is that? Well, I mean, the Heegaard Floer complex is generated by tuples of intersection points, and topologically, the tuples of intersection points are exactly the same because I just switched calling the alpha and beta. And then, well, if you think about the sort of disks, well, the disks here are almost exactly the same as the disks here. But the thing is, you remember we have this boundary condition on the disk, which is maybe the right-hand boundary maps to T alpha, like the alpha torus, and the left-hand boundary maps to the beta torus. So if I flip the alpha and beta curves, and of course I sort of have to reflect the disk. And if I reflect the disk, then it becomes anti-homomorphic with respect to the original almost complex structures, which is why I've sort of conjugated the complex structure over here. Okay. So the point is that between h and h bar, there's sort of an exact correspondence of generators and disks. So this is a chain map, which is an isomorphism. This J here. Okay. So this is great, but this J map does not. You know, it doesn't quite go between this complex to itself. It goes between this complex and slightly different complex. And so the point is that now we pull out the heavy machinery. And the heavy machinery is that, well, OK, so let me extend the board to this board. So the heavy machinery is that, well, these are two Heegaard diagrams for the same manifold. So it doesn't matter which sort of data I choose. The chain complexes will be homotopy equivalent. Okay, so I choose some homotopy equivalence that goes from h bar back to h. Okay, so there are actually many such homotopy equivalences, but it's work of you certain that there is a preferred homotopy class of chain homotopy equivalence that goes between two different Heegaard diagrams. Okay. And now I define iota to be the composition of these two things. Okay, so this is something that goes from this complex back to itself. YH back to CF minus of YH. Okay? And the idea of Heegaard Floer or involutive Floer homology is exactly just I want to use the additional data of this map here. Okay, so note that this map is not an exact involution. Why is that? It's because this map, this annoying homotopy map here, is very mysterious and comes from handle slides and things like that. But it turns out that iota is a homotopy involution. So it doesn't square to 1, but it squares homotopic to 1. Okay. All right. So let me. Let me make some definitions. Okay, so I'm going to define for you this notion of iota complexes and local equivalence and so on. So first definition is, so an iota complex. Okay, so this is going to be a pair C comma iota. Okay, so C is a chain complex over F adjoint U. So okay, so everything here will be with Z2 coefficients. So F is Z by 2. Okay, so Z by 2. It's Z graded, freely generated over F of U. And it has this important property that when I look at the homology of C and I invert the action of U, then this is isomorphic to a single tower. Right, so this condition is just saying I have one U non-torsion element in the homology of my complex. Right, this is reflecting the fact that if I have an integer homology sphere, then the infinity HF is a single tower. Okay? And iota here is a homotopy involution. Okay? So iota squared is homotopic to 1. And iota is grading, preserving, U equivariant, so on. Okay? So this is just the formal definition of an iota complex. Okay? Let me make extra definition, which is that if I have two iota complexes, C1 and C2 iota 2, these are homoequivalent. What does that mean? That just means that, well, C1 and C2 are homotopy equivalent in the usual sense, where I have chain homotopy equivalences between them. Okay, but I require that these chain maps commute with sort of the iota maps up. They have to play nice with the iota maps. Okay, and so the condition is that so like this. Let's see. So this is a natural notion of homotopy equivalence between iota complexes. And so, of course, the theorem is that, so the theorem of Hendricks and Manolescu is that if I have some y here, let's say an integer homology sphere, then, you know, minus of the Heegaard Floer with this iota map that I've defined for you, this is a well-defined, you know, procedure up to the notion of homotopy equivalence of iota complexes, right? So I could have chosen a different Heegaard diagram. I could have chosen a different representative of the chain homotopy equivalence. But all those choices change the resulting iota complex up to homotopy equivalence. Okay. Are there any questions about the construction? So I should note that technically, invariant Floer homology proper is defined to be you take take the homology of the mapping cone of this complex with respect to 1 plus iota. This is what is called the invariant Floer homology. In this talk, we will only ever talk about the actual iota complexes. And when I say invariant Floer homology, I will just mean sort of this data. Okay? All right, now let me introduce one more definition, which is probably the most important definition. So this is one more definition, which is two iota complexes are locally equivalent. Okay, so this is going to be sort of an equivalence relation which is coarser than the relation of homology, or homotopy equivalence. What does this mean? Well, as before, it means that I have these chain maps, grading, preserving, U equivariant maps between C1 and C2, and they commute with the iota maps up to homotopy. So this is I2F, and then I2G. Okay, but now these F and G maps are not homotopy equivalent anymore. Okay, so the condition on these F and G maps is that when I look at their action on homology, okay, and I invert U. So remember, this is, both of these are just towers. The requirement is that these F and G maps induce isomorphisms between these towers. Okay, so this is the same thing as saying that these F and G maps on homology, they take U non-torsion elements to U non-torsion elements. Okay, so I'll give an example of this notion and some idea of what this notion really means in just a moment. Okay, but the point is, of course, the theorem is that if I have two homology 3 spheres, which are homology cobordism, then turns out that their iota complexes are equivalent in the sense of local equivalence. Okay, that's the theorem. Okay, so and then just to sort of finish up the story, so theorem Hendricks, Manolescu, Zemke. So a couple of things. So so the obvious notion of tensor product on iota complexes is I tensor product the complexes, and I tensor product the homotopy involution. And this gives me another iota complex. And it turns out that the tensor product gets well defined with respect to local equivalence. So if I change something in its local equivalence class, then the outcome of the tensor product also changes in the local equivalence class. And so the theorem, let me just state it again, is that when I take the connected sum, it maps to the tensor product of iota complexes under this taking of iota complexes met. Okay? And so, again, the group J I mentioned earlier is this set of iota complexes modulo this notion of local equivalence. Okay? So inverses in this group, maybe I should say inverses in the group are, if you have an iota complex, you can construct a dual iota complex by dualizing the complex and dualizing the iota map. This is another iota complex. And taking duals is inverse in this group. Okay. All right, so have any questions about the definition? All right, so maybe I will write some examples which will sort of make these notions clear. So let me just give you some examples of iota complexes. So the stupidest possible example, so let me talk about the iota complex associated to S3. So the complex, the CF minus complex has only one generator. It has a single tower. Okay, so let me draw it like this. Okay, so it has one generator in grading 0, and then U powers of that generator, which I am representing by this, this tower here. Okay. And well, there are not many homotopy involutions you can put on this thing. So the action of iota will just take the generator X to itself. Okay? This is trivial iota complex. As you can guess, this is the identity element of the group. Okay, so maybe the first slightly less trivial example, let me do sigma 237. Okay, so what does this look like? Well, so the Heegaard Floer complex is generated by 3 generators. Okay? 2 of them are in grading 0. So let me call them V and iota V. So these are in grading 0. And then the third generator is in grading -1. So, so let me call this generator alpha, and it's in grading -1. And the boundary of alpha is V plus iota V. Okay, and the action of iota takes V to iota V and vice versa, and the action of iota fixes alpha. Okay. So this is another very simple complex with 3 generators. Okay, so maybe just, let me just, for completeness, let's think about the homology of this complex. So if I take the homology of this complex, the usual Heegaard Floer homology, then it looks like this picture. Okay, so in this picture, by the dots, I mean generators of the homology, and the lines are supposed to represent the action of U. So when you take the homology of this, in grading 0, I have 2, the Heegaard Floer homology of rank 2, and then both of those generators, if I multiply by U, they become the same because they become homologous via alpha. Okay? All right, so these are just some basic examples of iota complexes. Let me try to give you some intuition for the notion of, where did I write it? Of a local equivalence if you've never done it before. Okay, so let's think about the notion of local equivalence. Well, okay, so first let me forget about the iota maps. Okay, if I forget about the iota maps, then the relation of local equivalence is, do there exist chain maps such that on homology, they take U non-torsion elements to U non-torsion elements? Okay, grading preserving. And the claim is that this is sort of just the usual relation you get in usual Heegaard Floer homology when you have a homology cobordism between 2 things. Okay, because in usual Heegaard Floer homology, you probably know that the D invariant is homology cobordism invariant. But the D invariant is computed by looking at the maximally graded U non-torsion thing in homology. So if you think for a little bit, then you will see that saying that D invariant is the same is really very similar to saying that these F and G maps take U non-torsion elements to U non-torsion elements. Okay? So the point is that the additional thing coming from involutive Floer homology is just the extra requirement that these maps play nicely with respect to the involutions. Okay? So let's look at this particular example. So again, let's forget about the involutions. Okay, so can I construct maps F and G between these complexes which are isomorphisms after I pass to the infinity version? Well, the answer is yes. So from left to right, I could take X to either V or iota V. And that would sort of embed the homology of S3, which is a single tower, into this homology starting at either the left or the right, sort of topmost leaf, respectively. And the opposite direction, I could take both v and iota v to x, and I could take alpha to 0. And that would be a well-defined chain map, grading preserving, takes u non-torsion to u non-torsion. So the point is, from the viewpoint of regular Heegaard Floer homology, these two spaces might be homology coborded. I mean, the d invariants are both 0. Okay? But you see that the map from the left to the right is not iota equivariant. It breaks the iota symmetry. And there's no way for me to construct such a map, even allowing homotopy, commuting up to homotopy with iota. So the point is that the involutive Floer homology, this local equivalence, forbids these two things, homology coborded. Yeah, there are lots of ways you could say this. You could say it using the involutive Floer correction terms and so on and so on. But those are really just shadows of this argument. Are there any questions about the example? Let me see. How much time do I have? Well, I put my phone somewhere, so I don't know. What? What? OK. Very good. OK, let's see. All right, so this is sort of an overview of involutive Floer homology. So now I want to talk about the next. Now I want to talk about the theorem, which is this computation of involutive Floer homology. So involutive Floer homology of Seifert fiber spaces. Okay, and instead of trying to go into the details of the proof of the theorem, I sort of would rather talk about sort of the decomposition algorithm that I alluded to, where if you give me a sum of Seifert fiber spaces, I can tell you its image in the Z infinity. I mean, I have to convince you that this is a practical thing to do for this result to be useful. All right, so, but before I do that, so maybe I should, so if you remember, I said that we have an explicit basis given by the image of certain B-square spheres, so I'll just tell you what those complexes look like. So it turns out that H of, so remember, yi, which is H of minus 1, 4 minus 1, maybe this is a plus actually, 4i plus 1. So what does this look like? Well, actually, it looks very much like sigma 237. Okay, it also has 3 generators over f of u. The top 2 generators, which I'll also call v and iota v, they live in grading 2i. And then there's some generator alpha, and this generator lives in 1. Okay, and the boundary of alpha. Oh, sorry. So I actually made an error here. So well, happily I didn't write it down. So the I think I said the boundary of alpha is v plus iota v, but it's u times v plus u times iota v. Okay. So the boundary of alpha here is some u power, the appropriate u power of v plus the appropriate u power of iota v. Okay. So when I take the homology of this, again, it looks very similar. So instead, I get, so before I had some sort of pitchfork-looking thing where these sort of prongs had one edge in them. And now I have some pitchfork-looking thing where the prongs have I edges in them. So really, in this picture, I should draw a bunch of vertices to represent the generators of the Heegaard Floer homology, but I've suppressed drawing the vertices. Okay. All right. So these are okay. So and also y0, which is the image of the Poincare homology sphere, is just the trivial complex, but I shift in grading by 2. Okay. The topmost generator starts in grading 2, okay? And it turns out that tensoring with that complex has the effect of shifting the overall grading. So really, I'll just think about the basis as consisting of these elements here. Then I allow overall grading shifts, okay, which can be affected by tensoring with the Poincare homology sphere, okay? All right, so these are the basis elements. Okay, so given a sum of Seifert fibered spaces, how do I compute for you its image in the Z infinity? All right, so let me sort of outline the algorithm, okay? And the outline of the algorithm will actually say a few words about the proof of the result. So step 1. So the first step is, so compute the symmetric graded root. Okay, what does this mean? Symmetric graded root. Okay, so what is a symmetric graded root? Okay, so instead of carefully writing down the definition, I will draw a picture. Okay, so the picture I'm going to draw, let's say, like something like this. Let's say, and then I can add some things here. Okay, what is a symmetric graded root? Okay, so, well, a symmetric graded root is just some like infinite tree, okay, upwards opening tree, and it has an infinite stem below, okay, and the tree has a lot of vertices, which I've suppressed drawing, just like in that tree. And the vertices have a grading, which is represented by the height, okay, and the grading takes values in the even integers, okay? And the symmetric part is just saying that it's symmetric about reflection across the sort of vertical stem. This is just like generalization of the picture I drew over there, okay? So this is a symmetric graded root, okay? And the curious theorem is that so if Y is a Seifert fiber space, okay, then up to orientation reversal, the Heegaard Floer homology, the minus version of Heegaard Floer homology of Y, is a graded root, or symmetric graded root. Okay, what do I mean by is a symmetric graded root? Well, I just mean that it has a presentation where, you know, if I can do this as an f of u module by saying each vertex is, you know, a generator over f2, and then the edges represent multiplication by u, just like in this picture, okay? And so the theorem is that actually, for a Seifert fiber space, the Heegaard Floer homology is always of this form, up to orientation reversal, okay? Why is this theorem true? Well, okay, the reason is probably not very enlightening to people who don't already know why the theorem is true, but so this theorem is due to, more or less, Osvath and Szabo, and also András Nemeti. Okay, and the way the theorem is proven is that if you have a plumbed, or a plumbed three-manifold, or maybe certain class of plumbed three-manifolds, you can form a completely combinatorial invariant coming from the plumbing diagram. Okay. And this invariant takes the form of a chain complex, and you can take the homology. And it turns out that homology, you can prove that is isomorphic to the Heegaard Floer homology in certain nice cases, including the case of Seifert fibered spaces. Okay? And this is a completely combinatorial construct. There's no homomorphic anything. Okay? And the lattice homology, so that the name of this thing is the lattice complex, and the homology is the lattice homology. And the lattice homology almost sort of manifestly takes this form. Okay, and that's why the Heegaard Floer homology takes this form. Okay, so the lattice homology tells you the Heegaard Floer homology. This is not relevant to the decomposition algorithm, but let me point out a few things how we sort of proved our theorem. So turns out that the computation of the lattice homology does not just tell you the Heegaard Floer homology, okay? Because there's this symmetry, there's sort of an inherent symmetry in the lattice homology. There's this involution across the vertical stem. And it turns out that that involution coincides with the homological action of iota on the Heegaard Floer complex, okay? So symmetry in the graded root under the isomorphism between lattice and Heegaard Floer homology actually corresponds to the homological action of iota. Now remember, iota is a homotopy involution, but of course when I pass the homology, it's an actual involution. Okay? So computing the lattice homology tells you a little bit more than just the Heegaard Floer homology. Okay? And so this is the point at which you sort of get to cheat. Okay? Because it turns out that four complexes of this form, if you know the homology is a graded root, and you know the involution is this reflection across the sort of stem. So another theorem is that in such cases, the knowledge of the homological involution actually fixes the action of iota on the chain level up to homotopy. So this determines the actual iota complex, right? And basically the point is, well, okay, so the point is, well, I sadly erased it, but if I told you that I want a homology, which is this, and the induced action of some homotopy involution is this, then the complex that I wrote down before is the most obvious complex that you could write down that has those properties. And you can prove that it's an algebraic fact that that complex is the correct complex up to homotopy. Any other choice of complex will be homotopy equivalent to that one. Okay? And so this is actually true in the case of Seifert fiber spaces in general. Okay? All right, so the point is so this is how we do our computations, because we sort of have an explicit model for the iota complexes for Seifert fiber spaces. Okay, that's how we prove our theorem. Okay, but sort of back to this decomposition theorem. So the first thing you do when you, so maybe I should have said so. So here, let me just start with a single Seifert fibered space. So the first thing you do is you compute this graded root. And then so step 2. Okay, step 2 is extract monotone subroot. Okay, so again, I'm not going to give a precise definition of what is the monotone subroot. Instead, I will again draw a picture. Okay, so a monotone root is a special, type of graded root. Okay, and it sort of looks like this. Okay, sorry, my picture is not the greatest. Okay, so it's a symmetric graded root, but it's sort of a spindly tree. Okay, so each branch has no other branches, and each branch point sort of has at most 2 things coming out of it. And the condition of being monotone means that sort of the leaves, as I move outwards from the stem, go upwards in grading. Okay, this is the definition of a monotone root. Okay, and then it's just, so then there's a sort of very simple theorem slash lemma, which is that any symmetric graded root has up the isomorphism a preferred monotone tree sitting inside of it. Okay, and let me just do by example. So what you do is you just do some sort of greedy algorithm. So you sort of start from the sort of innermost thing, the innermost branches, and you include branches whenever you can so that you get a monotone subroot. So in this example, this green here is the monotone subroot of this graded symmetric root. Okay, right. So this is a very visually obvious combinatorial procedure. If you give the symmetric graded root, then you can just visually extract the monotone subroot from the graded root. Okay, and then, so this is the second step. Okay, and the last step, well, so actually it turns out this is basically it. Okay, so the last step, the step in which we profit. So the last step is I just look at the monotone root here. Okay, I do the following. So I look at all of these branches, okay? And I write down the lengths of the branches, like how many edges are in each of these branches. Okay, I've colored them green in this picture. Okay, and then I draw a bunch of lines on this thing which connect sort of successive sort of branch points with successive leaves. Okay, so I draw a bunch of orange lines, like something like this. In this case, there's a degenerate thing where I draw an orange line like this. And I look at the lengths of all the orange things. And by lengths, I just mean, well, I take the grading difference of this and divide it by 2. Okay? And finally, I also make a note as to what grading this sort of like uppermost sort of thing on the stem lies. Okay? And then to get the decomposition into the Z infinity basis, what I do is I just, for each of the green lengths, I just write down the basis element whose index is the corresponding length. And then for each of the orange lengths, I subtract the basis element whose index is the corresponding length. And then at the end of the day, I just take my expression and I shift it in grading according to the grading of this uppermost thing on the stem there. And that's it. Okay? So if you give me one Seifert fibered space, the way to get the basis decomposition is I compute the lattice homology and get this. I visually extract the monotone root and get this. And then I just write down this sort of alternating sum, which depends on the lengths of these things. Okay? And then, of course, if I have a sum of Seifert fibered spaces, then I just do this to each term. and then I add them all together. Okay? And that gives me the decomposition into Z infinity. Okay? Let me see, how much time do I have left? I actually have 12 minutes left. Okay. And so this is actually most of what I wanted to say, but let me say first, are there any questions? So maybe I will just about how we proved our theorems about the Rokhlin invariant and the Neumann-Sieben invariant. So this is probably more useful to people who sort of already know a little bit about lattice homology and the Neumann-Sieben invariant. So how do we prove that? So the theorem that I want to talk about is the theorem that I said before. So the Neumann-Sieben invariant is a well-defined invariant from Seifert fiber spaces. It's homology cobordism invariant for Seifert fiber space. How do we prove this theorem? Well, the thing you do is first you just look at one Seifert fiber space. So suppose Y is a single Seifert fiber space. Okay, and what you show is that you show that for one Seifert fiber space, the Neumann-Sieben invariant is equal to some other invariant, which is defined in the involutive Floer homology. Okay, so you prove something like the Neumann-Sieben invariant of Y. So there are some factors of 2 and minus signs that I'm omitting, is more or less equal to something like the D lower invariant of Y, or something like this. Okay, this is not an exact equality. There's some factors of 2. And how do you prove this? Well, so there are a couple proofs of this fact. The first one, due to Matt, is sort of in the monopoles case. It uses, I think, an explicit computation of some index due to Ruberman and Savelyev. But if you know a little bit of lattice homology, then actually this is not a very surprising statement, because the Neumann-Sieben invariant is defined in terms of this plumbing. It's a combinatorial invariant defined in terms of the plumbing. So if you believe that Heegaard Floer homology can secretly be computed by some combinatorial thing, which is determined from the plumbing, then it's not very surprising that actually you can identify some homological invariants as sort of combinatorial invariants defined from the plumbing diagram. Okay? So you sort of establish that you can read the Neumann-Sieben invariant from the involutive Floer homology in the case of a single Seifert fiber space. Okay? And then you just establish that reading in such a way such that you define it in terms of the Z infinity basis. Okay? And so then you're basically just constructing a new homomorphism out of theta SF to Z, which is defined in terms of the Z infinity basis. And you already know that it agrees with the Neumann-Sieben invariant on individual Seifert fiber spaces. Since the Neumann-Sieben invariant is additive, then you know that it actually agrees for all linear combinations of Seifert fiber spaces. Okay? All right, so that's actually all I have to say. I don't know. Are there any questions? Okay. Sure? Okay. What? Sure? Yeah, so I said this in terms of Seifert fiber spaces, okay, but actually it's true for a larger class of integer homology spheres like AR homology spheres. And also there's also a form of the theorem, rational homology spheres. Yes, so the answer is yes. Sure? Okay, so that's a great question. So, the better answer to this is, so what does it really mean to be in this H of theta SF? So the cleaner way to think about it is there's this connected Floer homology defined by Hendricks, and Manolescu. And I've just told you that we sort of explicitly understand the involutive Floer homology of theta SF. So from that, it's in a different paper, but from that theorem, you can compute the form of the connected Floer homology for all sums of Seifert fibered spaces, and it has a particular restricted form. And so the thing to do is to say, well, anything not of that form in the connected Floer homology must be. Okay, but to answer the actual question, so in the connected Floer homology, So for example, if I had a connected Floer homology, which let's say has two torsion towers. Okay, so this is sort of the non-torsion tower here. And it has two torsion towers. And one is an even grading and one is an odd grading. And the length of the first torsion tower is shorter than the length of the second torsion tower. And actually, any such thing is not a sum of Seifert fiber spaces. So actually, you can get very simple. The condition is actually quite restrictive. Okay? So there are lots and lots of complexes, for example, which have this. I don't want to write the actual complex down because it's sort of complicated. But there are lots and lots of complexes which are not. But of course, then the question is, like, are they realized by actual three manifolds? And we don't really know. Step 3? I mean, right, so this is the heart of the paper, which is that, so I'm not really going to answer this question, but the point is that, well, so in the example I gave before, then you see that if I give you two iota complexes, to determine when there's a local equivalence between them, it's just some terrible combinatorics game where I search for the presence of these F and G maps. And the point is, we have, this explicit model of the iota complex of a Seifert fiber spaces, and just expand the iota complex of this huge tensor product. Okay, but this is actually very difficult because this is humongous, right? This is going to have 3 to the n generators, where n is the number of terms here. So we developed some actually pretty, sort of maybe sophisticated combinatorial, sleight of hand. So it turns out that you interpret these things as sort of lattice-like pictures, and then you have some geometric intuition for what the F and G maps are supposed to be, and then you establish it. But it's a long combinatorial computation, basically. That have this? I guess opinions are split. I don't know if Matt believes there aren't. I think we certainly believe that it's not true that theta SF is equal to theta, but I'm not sure whether you can detect it using the involutive Floer homology. We don't know. There are manifolds you could try, two bad vertex manifolds, and so on, but we're not sure.